Go.
Okay, so we're analyzing rotations. Why? Because they're useful. They're very useful. We can talk about planetary systems, we can talk about stars that spin, planets, moons, things that orbit. So it's useful on an astronomical scale. It's certainly useful also on the scale of just pulleys. We've got things like spinning disks. Why is that important? Who cares about this thing? Well, because we've got machines and motors and things that turn and spin around and all these different rotations and wheels going on here. So we need to understand this stuff. There's good news and there's bad news. The good news is the theory is very similar to what you've learned. And so consequently, it actually acts as a review if you think about it right. The bad news is it starts getting a little tough to have an intuition for what happens. Consequently, a lot of the demonstrations are kind of cool, like, whoa, I didn't expect that to happen. Okay? But there's more good news. And the good news is that sometimes when your intuition fails, the theory will guide you. So if you start with the basic theory, lay out what you have, then you'll get your result. You carefully draw your pictures and do that, you'll get there. That's very true of modern physics or really 20th century physics of relativity and quantum mechanics. So you start learning that these are very powerful tools. We develop these general theories for analysis so that we can relate things like time intervals that we measure, lengths that we measure, masses that we measure. Okay, so let's talk about this real quickly here. We're going to analyze rotations, and as a review, we used energy analysis. That's good. We can use kinematics analysis. We can use a torque analysis along with force analysis. But with an energy analysis, we just took a chunk, a small chunk, something smaller than that R, spun it around and said, hey, that's got kinetic energy because it's moving. It's got the ability to cause change due to its motion. That's 1/2 mv squared. But wait a minute, V is R omega because it's rotating. So I'm going to turn it from translational terms into rotational terms. Why? Oh, because it's kind of useful, right? So it's really the same thing. But when you change a theory in terms of ideas that help you think about it that way, rotationally here, it can be useful and easier to calculate. So V becomes R omega. And then you go, hey, what if I group the M and the R squared? Well, that's something we call rotational inertia or moment of inertia. And you can look up those words. Omega squared. So 1/2 resistance to alpha times the angular velocity squared. So that's nice. And you just put that in with all the other types of energy. So you can also do this with work. Work is a concept of energy. It's a way to change energy. You can exert a force so as to speed an object up, or at least try to, adding energy, so as to slow it down, or at least try to slow it down, that would be taking the energy away, or just to turn it, which doesn't change the energy of the system and does no work. So the work from a force happens not at a state, it's not a state variable, it happens between two states, an earlier and a later state. Now, rather than, I could write this, of course, as an integral, or I could just say it's the force parallel to the path times the distance along the path, or the displacement along the path. You can see the units here, Newton meter, joule, fine. So I write that F parallel times, hey, wait a minute, S along the path. Now I'm looking at rotational things. So this little picture goes a long way. Let's do a little teeter-totter here. If S is along the path, then S is R delta theta. All right, so I can do S is R delta theta. Now applying it to this sort of case. Well, I can group them again. I can pull the delta theta out, F parallel times R, this times that. That's not work because we're not moving a distance R. Right? So that times that is actually not a joule. This is a joule. This is not. That is a torque. And again, the difference is R versus S. And so I've got work can be written in terms of torque delta theta. It's still the same idea. It's still the same thing, but I'm changing it. That's clever. It's useful. but it's a little challenging conceptually. So we got to start letting our theory guide us, and we get used to it, and we can, of course, integrate the torque over some angle d theta in units of, here, yes, this is not a joule. However, this product here would be in units of joules and can be included just as before. Now, momentum analysis is also useful. As we saw, momentum analysis is very useful in collisions over short time intervals or explosions, short time intervals, very useful. But they can be used a variety of ways. But that's true here with rotational stuff. So what I've drawn here is parallels between the old, so it's a nice time to review since final exam is looming, and the new. And it really sinks in when you've gotten more familiar with it. So what I've got are definitions. Newton's second law relating to net impulse causes a change in momentum. Net force causes acceleration. Newton's third law for free collisions, that's my shorthand way of saying things aren't held in place or there aren't other forces that are affecting it during that short time interval of the collision, giving conservation of momentum. Okay, so you're probably very familiar with that. So let's go side to side here. Let's look at the definitions, and where they come from are these laws. So the definitions, I want to write this out. It's kind of messy. I need to talk about the momentum of an object. You can call it object R, object A, whatever. The momentum of an object is, by definition, the mass of that object times its velocity. And I've written here this one to say, well, that's the momentum at some instant. So that is a state variable. It's I got momentum now, and momentum now, and momentum now. Now that's nice because you can write that short, and that's beautiful because you don't have to do it this way. But until you can keep it that way until maybe you analyze it. So usually we'll break the vector down into x and y parts. Now I've got the momentum of A at state 1, x component, momentum of A at state 1, y component. So the subscripts get kind of messy. Just lay it out however you do it and be kind of clear. That's getting a little bit crazy. But nonetheless, momentum is a vector. And that means I've got to choose some direction, whatever it is, plus x and plus y, something. And I've got to show it so that I know which way is plus and which way is minus. All right, cool. That's what momentum is. Inertia times velocity. Impulse, that's what causes change in momentum. You know, that's just, again, redefining it in terms of angular, or in terms of different terms here. Rather than talk about net force, I'm going to talk about the net impulse over here. So the impulse from any force on an object is, by definition, the average force over the time, or you can write that as an integral, or the graphical area between the force and the t-axis, the force curve and the t-axis, however you do that. But remember that you've got to break vectors into parts. So impulse has an x component and a y component. Okay, so it's like that. All right, so what are the, well, let's go down here. Let's go down here, that'd be nice. So where does that come from? That comes from the net, Newton's second law, net force. You got to include all of them. On, so this has got to be on. I've got to choose my receiver, whatever object, I could say. So that would be the mass of R and the acceleration of R, not a force. Mass of R, change in velocity of R. Of course, that's a vector, so I'd have the x part separate and do the y part separate. Now you guys have really got this down. It's confusing at first. So I can play around with that, and I can rearrange that by integrating f over time equals m delta v. Now, I'm not going to put this on here right now, but mass can be changing. If your car driving down the road, you're using gas, and some of it's going out the exhaust, so your mass is changing. In a rocket, the mass is changing quite a bit. So what this was really written as was force net is equal to, dp dt, where p is mv, and that allows for the rate of change of mass, dm dt. So you take the basic idea which we've been building, and you start getting a little more theory, and you start letting that math guide you, with an inkling of intuition, sometimes losing that intuition. But nonetheless, we can reframe our theory, and I think that's really important. You can see lots of demos on the web and lots of cool stuff, and it's fun. But understanding how this is tied in is a cool thing. So I've got net impulse causes a change in momentum. In this case, letting the mass stay the same, so I'm just changing the velocity. All right, cool. And then Newton's third law, what we did, we developed this idea, this method of analysis called conservation of momentum. And if the objects are free to move, not too much friction on the interaction, external stuff, then the force from object B on object A, we know is equal in strength but opposite in direction, Newton's third law, to the force from A on B. You know that. We know that if just those two are interacting, then we've got a time of collision or explosion that's the same for A as it is for B. They experience the same thing. And so we did that analysis, and I won't redo it here, but that leads us to the law of conservation of momentum. But it must be done in separate x and y directions, right? Unless you've got another clever way, or maybe it's just one-dimensional, which is nice. So that means that there's no change in momentum in the x. The total momentum of A and B, x components, just after the collision or explosion, minus the momentum of A and x, B and the x just before, 0. No change. Now you can move that over here. You can write it however you want. Doesn't matter. This is the concept, that there's no change. And this is the reason why. Okay? And then you could do the same thing for A and for B, but you have to use the y components. So throw in their cosine of whatever, sine of whatever, your pluses and your minuses in there, straighten out, and then do the algebra. So that's the theoretical framework. When you get used to it, you just draw your picture, throw it in, and you have the understanding rooted in these laws. Okay, so now we can do this for rotational stuff. Okay, so for rotational, it's the same idea, but again, the intuition gets a little more abstract. And on top of that, we can talk about spinning rings, or we can talk about chunks. Now that's a pretty big chunk, but I could take even a small chunk. So this is interesting. We'll talk about this after we do this little video on the theory. And this is an introduction here, so just kind of go with it, and you know that you're going to work with it, and that's when you really get it. But here it is. If I take a small chunk, and by that I mean kind of like I did over here, just some bit here, traveling along, mass here, velocity here, and it's kind of weird to say that that would have angular momentum. What do I mean angular? Well, remember rotations, we talked about the axis of rotation, or the axis of rotation, or the axis of rotation, or the origin sometimes called, the point around which we're looking at the rotation. So if an object is coming towards me and I were to be pointing at it, it wouldn't be going around me. If an object was going straight, but over here, along this line, and I pointed at something driving by, maybe there's a car there driving by, I'd go, hey, look, there's the car. And so it would be going around me. Even though it's going straight, the car is going around me. Oh, here it is. Now it's going around me the other way. So something can be moving straight. Now, is it spinning? No. But we have a theoretical framework that allows us to use that. And so, I told you, the intuition starts getting weird, right? I mean, something spinning, that's, fine. Angular acceleration, that makes sense. It's got some angular acceleration. But something just moving in a straight line? Well, it's a good way to analyze it. And you got to do some problems to realize, hey, that works out pretty neat. I'm not really talking about anything different. Okay, cool. So I could talk about little chunks, or I could talk about extended objects, rods, rings, discs, spheres, rotating. All right, just go with it. Trust it, play with it. But when you do your problem, just go, okay, I'm just going to use this. I don't I'm not as comfortable with the meaning up front. So what's the angular momentum? Well, again, we have a little bit of an issue because we can talk about direction for rotation two ways. And you need to get introduced to this. For me, this is, let's see, counterclockwise or clockwise? Counterclockwise. For you, it's the other, right? And I can call that plus or minus. Here's the other way. For me, this is clockwise. For you, it's counterclockwise. So the way that's fine if we're both on the same side. Oh, look, we both agree. It's counterclockwise and it's clockwise. Okay? And that's the way it's really moving. The right-hand rule says, make your fingers curl with the rotation. Right hand only. We could have done the left hand, then we get the other way. And that tells you, if I use the left hand, I get this way. If I use the right hand, I get that way. So it's made up. But it's a really clever bookkeeping device. It works, you get the right answer, except the intuition starts getting lost. So if I go like this, I get towards you. If you go like that, you get that way as well. And so we both agree. So when we have complex rotating systems where the axis is even changing, we need to use that sort of abstract definition. There's nothing physical. So what we say is omega, the angular velocity, is that way. And the angular momentum is that way. It's not that way, but it's a good bookkeeping device. Okay. For me, hey, it's clockwise. For you, it's counterclockwise. So we might have a disagreement. If we use this, we'll get it right. That's very similar to how you define mathematically a plane, a flat surface, by using the line perpendicular to a plane, the equation for that. Okay, so what's the definition? Well, it's kind of like torque is R cross F. Angular momentum is R cross momentum. Or, if you use plus and minus clockwise, counterclockwise, which you do anytime you can, then it is R, momentum, mv, good old mv, times the sine of the angle between those two. We know that P and R are vectors, but here we just need the amounts. So you need to explore those. Just go with it, relax. Look at the units. Meters, kilogram, meter per second. Kilogram, meters squared per second. Just explore it, okay? Or, again, we can use that right-hand rule, so we can use the angular momentum as R cross P. Either way, it's a very similar definition. The only difference is which way we're using as plus minus. Okay. R is from the axis or origin to the object, in this case A, which is a tricky thing because I often call my axis A. Now I'm calling my object A, and I just want to point, whatever, make up the names. Make it up, draw your picture, lay it out. It's a puzzle. That's what we do as engineers and science folks. So that's for a small chunk. You can actually talk about the angular momentum of an object that's moving in a straight line. Silly, crazy, but it's relative to you. So relative to you, that thing is going around you, right? If I go like this and I drop it, hey, it's going around. It's going around this point. Okay? All right, so now for an extended object, what do we have? Angular momentum is, well, it's kind of like mv, isn't it? But it's I omega. So you'll see that the units are different than P. Kilogram meter squared, radian per second. Kilogram meter squared per second. Kilogram meter squared per second. These are the same, they better be, their angular momentum. So object B, maybe it's a rotating disc or sphere or ring. This is the easiest way. So if you can use counterclockwise, clockwise, do that. But when we talk about gyroscopes and things like that, you can't keep track of it. And so you're forced to use this more abstract right-hand rule direction. And we say omega, direction of omega of something spinning. is given by the right-hand rule. Now it spins the other way. Omega is this way. No, it's not, but it's a good bookkeeping device. Right? That's all it is. So you go with it. Yeah, this is a little unsettling. It's a little less intuitive. Yeah, it is. It's fine. So either way, but use this whenever. Now that can be plus, or counterclockwise could be -2. It's fine, whatever you choose. Frequently counterclockwise is chosen as plus. So that's angular momentum. It's a lot like mv, but it's I omega. Rotational inertia times rotational angular velocity. So it's familiar. Go with it. Relax, be bold here. Now let's develop Newton's second law. So what are the laws? They're pretty quick, and so I won't go into them too much. But if you remember the old, you have the new. And so we know that Newton's second law for rotations is the net torque equals I alpha. You can write that in terms of clockwise, counterclockwise around a point. So this would be torque around that point, rotational inertia around that point, angular acceleration around that point, which is I d omega dt, or delta omega delta t if it's constant. Or you can use the right-hand rule and just put that as a vector. It's the same form, so just don't make a big deal. It's not two different things. You're not memorizing symbols. You've got a relationship. There's Newton's second law for rotations. Great, you can rearrange that and you can figure out that the net torque over a time interval is going to be the change in angular momentum. So I can write this as delta L, can't I? Or delta I omega, more generally. And I said over there that we can deal with changing mass, like in a rocket. We often don't so much as an introduction. But here, a changing I is important. Because while my mass isn't changing, my rotational inertia is getting less when I pull in, or getting more as I go out. So changing rotational inertia is a very important part of our analysis. Again, clockwise, counterclockwise, or right-hand rule direction, same form, not a big deal. Don't use that unless you have to, but you do for some gyroscopes. Okay, so what about, this is the biggie. All right, conservation of angular momentum. This is very simple for introductory assignments. The problems are simple because we know that it's a little bit challenging conceptually. But just go with it. So learn to use your framework. Let's see. The torque from object B, maybe it's that one, on object A will be equal but opposite in direction to the torque from A on object B. And I can use the right-hand rule direction too. You don't even need to write it anymore. I'm either using that or that right-hand rule direction. So it gets to be less when you get more familiar with it. That means that there's no change in total angular momentum. And again, you don't want to do this for a big old mess. Energy is good for that. So that means the angular momentum of A plus the angular momentum of B minus the angular momentum of A plus the angular momentum of B. When? Well, just after minus just before. It's the change. In between those times, there was an interaction wherein the torques on one, from one on the other, is equal and opposite the reverse. And that gives us, in other words, finally, a thing to realize is this is going to be pretty easy initially. So again, on exams, some people will freak out and get 0 points. Other people go, well, let me just do this. And you'll see it's a simple calculation. You get 5, 10 points. And your friend didn't. And that's, too bad for your friend because really it wasn't that hard. So for instance, I've got something rotating. And I could drop something on it. And they interact, right? So what's going to happen? This guy's going to slow down. This guy speeds up. Let's do that again. So I can rotate. And if there's not much friction in the bearing, then it'll keep going for a while without noticeable slowing down. So I can think about omega, I can think about I can think about I omega, the angular momentum. This has no angular momentum. And now it's got some. Where did it come from? Well, because it got torqued by the friction speeding it up. But the friction on this that sped it up went the other way on the disk and slowed it down. Not that noticeably in this case, but the angular momentum before is L or I omega of, say, A.